In this session, we shall derive an expression for work done by an isothermal process. In case it has skipped your mind, an isothermal process is one that takes place at constant temperature. So right before us, we have an equation. We are following through from where we stopped in our previous session, that when we're dealing with work done by a gas that is expanding, it's given by change in work done, or that small change in work is given by P times dV. We know where this comes from our previous session. Now, of course, if we are to proceed with this, it means we're supposed to integrate it. And when we integrate it on both sides, this is integrating from 0 to capital W. This is integrating this thing from when, of course, it's changing volume, so it's from V1 to V2. We end up with W here giving us the integral of PdV from V1 to V2. But now, what if here we're dealing with an isothermal process. We are considering volume of a gas that is changed from volume V1 to V2. And the kind of gas we're dealing with here, we're dealing with 1 mole of a gas. So we are going to substitute for the value of P and put there. Since we are dealing with an isothermal process, an isothermal means it is constant temperature. We know that from here, this is P times change in V, and we know that PdV, that is PV, is going to be equal to R times T. So in the place of this PV, this is P times change in volume. Now, we might not have the pressure, but this is an isothermal process, and it being an isothermal process, we are aware of its temperature because it's happening at a constant temperature, and we are also aware of the volumes because it is changing from V1 to V2. So it means we can as well go ahead and substitute for that value of P, the pressure. From the ideal gas law, we know that PV is equal to RT. Of course, PV is equal to nRT, but the value of N here is 1. Since we are dealing with 1 mole of a gas, so this is 1 times RT. So PV is equal to RT. And when we make P the subject of the formula, this P, we end up with P being giving us RT over V. So we go and substitute this and put it right there. When you substitute this expression and put it right there, it means we are going to end up with our value of work giving us RT over V times change in volume. We know that R is a constant. We know T is also, since it's an isothermal process, we know that T is a constant value, and our value of V. So we go ahead and integrate. Remember, we substituted this from this point. So we shall continue with our integration from V1 to V2. So we shall go ahead and get the expression for the work done for an isothermal process. So this is going to continue like this. So this becomes work is going to be equal to, now integrating, this R is a constant, we only leave this, so we can put this RT outside the brackets. RT integral from V1 to V2. Now here I'm assuming that you are well versed with your integration from calculus, that is delta V. So of course for us this becomes RT integrating 1 over V from V1 to V2. We are going to end up with natural log of V. Natural log of V. The natural log of V is coming from V1 being the lower limit to V2 being the upper limit. So meaning that work done for is going to give us RT into, here we have ln natural log of V2 minus natural log of V1. And from here our value of work is going to become RT into, that is going to be natural log of V2 over V1. Of course, this is coming from our laws of logarithms, that when you are subtracting 2 logarithms of the same base, you simply divide this V2 over V1. So it means as far as work done for an isothermal process is given by RT times the natural log of the bigger volume over the smaller volume, and that is how we get the expression for work done for an isothermal process. Now this I've not explained much about this integration here, because I expect that by the time you're doing this kind of stuff, you know your calculus and you know how this integration flows. Now, like I had earlier said at the beginning of this video, here we are dealing with just 1 mole of an ideal gas. Of course, if we do not, it's no longer 1 mole and we are dealing with n moles of an ideal gas, of course, then that's when we introduce n there. W is equal to nRT. This is for n moles of an ideal gas. Now, from our work here, when work is being done by expanding gas, let's look at these two diagrams. If, for example, this is our V1. V1 means that is where the initial volume, V1. If this gas is expanding upwards, it means this piston is going to go and attain a new volume. And this new volume is what we are calling V2. This is what we've been following here. But then it is also possible that this is our V1, and probably this is moving downwards, and when it moves downwards, it means that our piston moves inside, and now our V2 is right there. So there is possibility that our V2 can be greater than V1, or our V2 can be less than our V1, the initial position of the piston. So in those cases, when these scenarios are happening, if you do not have a diagrammatic representation of what is taking place, but you're just calculating it right there, you just need to know that if V2 is less than V1, it means that there is a compression going on. And when the compression going on, it means that work is being done on the gas, or there is work being done against the gas, or work is being done on the system by the surrounding. On the other hand, if V2 is greater than V1, it means that work is being done by the gas, or you can say work is being done externally, or you can say work is being done by the system on the surrounding. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel, and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.